Greeting to all panels, I am Junwei. My undergraduate project title is Flight Dynamic and Control of a Winglet TAILLESS CAMAR UAV, which supervised by Dr. Suhaimi. Let us look into the content of presentations. First, introduction. Second, literature review. Third, methodology. Fourth, result and discussion. And finally, conclusion. Unmanned aerial vehicle, which is UAV, is a flying vehicle without a human pilot on board. This use of UAV is growing exponentially. Well, they originated mostly in military applications. Their use is quickly expanding to commercial. The enhancements of stability, performance, and efficiency of the UAV is vital and continuous research topic. CAMAR is a medium-sized UAV designed by the UTM researchers. The main goal is to be a high-endurance, autonomous, unmanned aerial system and terror, area observation and flight research facility. The application of UAV includes surveillance, search and rescue, law enforcement, geospatial analysis, agriculture, and forestry. Lastly, militarily related purpose. Next, the problem statement of CAMAR UAV is a TAILLESS configurations present a unique challenge from the perspective of stability and control. On conventional aircraft with vehicle tail, the maneuverability depends on the ability to generate the needed yawing moment, and then the TAILLESS CAMAR will lose its stability, especially in the lateral direction. The objective of my project is to design a linear, longitudinal, and lateral flight control system of a TAILLESS-WINGLET CAMAR UAV. The scope of my project is estimations of aircraft aerodynamics, stability, and control derivative of TAILLESS-WINGLET CAMAR UAV. Next, develop mathematical model of aircraft flight dynamics and TAILLESS-WINGLET CAMAR UAV. Lastly, design, modeling, and simulation of TAILLESS-WINGLET CAMAR UAV flight control system. Okay, the control and stability. An aircraft has to be controlled about its three axes, namely pitch, roll, and yaw. Pitch control means all control surfaces are deflect in the same direction as the conventional elevator. The roll control is achieved by either deflecting one of two control surfaces up on a wing and symmetrically down on another wing due to the lack of vertical control surface. And lastly, yaw control of directional control is taken care of the deflecting control surface on only one wing, where one control surface moves up and another down. The element flight control for pitch control is due to the elevator, roll control is due to the aileron, and lastly, yaw is due to the rudder. Static stability. When a pilot lets go the control in a level flight condition, a statically stable aircraft tends to continue its level flight path. Static stability refers to how moments created by aerodynamic forces and weight influence an aircraft in equilibrium. The longitudinal stability of an aircraft, also called as pitch stability, is referred to the aircraft stability is planned symmetrically about the lateral axis, which is the axis along the wingspan. In longitudinal stability, there are two flying modes. First is propagate mode, and another is short period mode. The lateral stability is stability of a moving or body or aircraft about an axis which is perpendicular to its direction of motion. In lateral stability, there are three flying modes. First, speller mode, dash roll mode, and also the road mode. Flight control system. There are two flight control systems. First, stability augmentation system is the system generally utilize pitch rate in the control law, and the sensor commonly utilized to measure its parameter are the radius. Control stability augmentation system, known as SAS or CAS, is a common part of modern aircraft control, and it's best categorized as a form of tracking control. Flying and handling quality. Flying and handling quality of an aircraft represent the easy and efficiency in which the aircraft correspond to pilot order to conduct the air operation or any mission task element. Let us look into the table of flying and handling quality. These two tables show that the minimum requirement of damping ratio or time constant in order to fly in level 1 of flying quality. Next, let us look into the methodology. This chapter will discuss the related methodology, outlook on the evaluation of stability and flying quality of TAILLESS-WINGLET CAMAR UAV. It will include the flying of aerodynamic dimensionless and dimensional derivative, followed by the wing and yaw controller design. This is the flowchart of methodology in this project. First of all, we find out the dimension and dimensionless derivative. Next, the stability and control derivative was obtained. Then we evaluate the flying quality. Then we design the system modeling and simulation. Lastly, evaluate the control system. Dimensionless and dimensional derivative. The conventional calculation of the stability derivative is first determining the dimensionless derivative, followed by the transformation of dimensionless derivative into the dimensional derivative. This is a simple method can be delivered to calculate the aerodynamic stability and control coefficients. Next, with the state space approach, the multiple equation can be solved simultaneously by written easily in the state space form. This application of state variable techniques to control problems can be called as the modern control theory. From the state space metric form, the SS2TF command has been used to convert into transfer function. The transfer function is developed by the TF command in MATLAB, and the PID controller manual tuning are designed in Simulink to obtain the optimization parameters. Lastly, the port placement. It is a majority of the design technique in model control theory is based on the state feedback configuration. The port assignment, or we call the port allocation, is placing the ports or eigenvalue of the closed loop system at the specific locations. Okay, next, let us look into the result. The longitudinal stability dimensional derivative. There are 16 dimensional derivatives that we obtain due to the Z-force derivative, X-force derivative, and pitching moment derivative. From the result of dimensional derivative, we substitute it into the state space metric form equation. We get this as our result. Then we transfer the state space metric into the transfer function form due to the aileron inputs, and then we plot the state response according each transfer function. After that, we obtain the eigenvalues, damping ratio, and natural frequency for the longitudinal stability. Basically, from the table we can see that the pursuit mode is unstable. On the other side, open loop short period mode is tactically stable due to the value of damping ratio is 0.502. It is still in the acceptable range for longitudinal short period flying quality, which is between 0.3 until 2. Okay, next, the short period transfer function is obtained by substitute the corresponding transfer function from the open loop transfer function of short period motion. It shows that the system is having a low stability condition where the damping ratio is 0.502 and natural frequency is 6 ratio per second. Next, let us look into the lateral stability dimensional derivative. We obtain the state space metric form same like the longitudinal method. We substitute the dimensional derivative into the equations. Then we get the transfer function form due to the aileron input and also rudder input. Next, this is the state response for the lateral stability, and from the eigenvalue, damping ratio, and natural frequency, we can show that the time constant of roll mode is 0.057 seconds, which can be classified as level 1 flying quality since it is below the maximum roll time constant. Meanwhile, the Dutch roll mode, the damping ratio is 0.294, above the minimum range of damping ratio, which also considered as a level 1 flying quality, but the spiller mode is unstable. So this is the Dutch roll transfer function that we obtain, and roll transfer function due to the aileron. Let us we look into the next topic. Application of classical control system is an application of automatic device. It's used to provide artificial stability for an aircraft that has been undesirable flying characteristic. Next, simple calculations show that how we gain the level of gains, which is K is negative 0.7138. Then we substitute into the characteristic equation again. We can see the loop occurs before and after closed loop feedback. The overshoot is lesser than the previous, which is 40.8%, and previous is 22.8%. After that, further step is to focus on the CAS outer loop design. The Ziegler-Nichols continuous cycling method has been used to determine the PID parameters by referring to the root locus of open loop system for the pitch rate. Okay, as this, the figure shows the block diagram of the classical control. From the observation, the Sweetener oscillations occur when the KPU, which is the gain, is 0.558 with natural frequency is 3.27 radian per second. The further calculation for the PID parameter are conducted to determine the value of KP, KI, and KD. As the result, we obtain the KP is 0.335 and 0.349 for KI and 0.08 for KD. The reference pitch angle was set up to 10 degrees and set time is 1 second. As you can see, the thread of Ziegler-Nichols method behave quite badly, which is the rise time reached to 0.62 seconds, settling time is 7 seconds, and amount of overshoot is around 10.87%. Hence, the manual simple tuning technique was used to tune back the PID parameter under constraint of specification. The new value of PID parameter are obtained. Optimization are KP is 0.487 and KI is 0.26 and KD is 0.044. With the new optimization, the design or control system now satisfy the requirements. The rise time is 0.2 seconds. Settling time only took 6.2 seconds, as the graph you can see. Okay, next, the application of modern control theory. In this chapter, the modern control theory is used to design an aircraft for the autopilots. As this simple calculation example, okay, you can see how we get the characteristic equations. We change it into the step feedback equation. Okay, the characteristic equation need to meet the desired specification. Damping ratio is more than 0.7 and the minimum natural frequency is more than 1 radians per second. So we took the damping ratio is 0.8 and the frequency is 3 radians per second to create the desired characteristic equations. Okay, from above figure, it shows the response of CAMAR UAV with the step feedback application. It only took 5.73 seconds for the system to become stable, and the system is much faster and it get rid of the steady state error, making the system to have almost 6% of overshoot only. Okay, next we apply the similar method to against the characteristic equations, but we change the damping ratio to 0.3 and the rate frequency is 1 radian per second. Create the desired characteristic equations. From above figure, it shows the response with the step feedback application. For yawing angle controller, it only took 3.7 seconds for the system to become stable, and the system is much faster and making the system have almost 7% of overshoot. Okay, same goes with the roll controller. As the result, we can see the step feedback application took only 3.3 seconds for the system to become stable and making the system have almost 5% of overshoot only. Okay, last but not least, the conclusion of the result and discussion reflect the result from the both methods. The controller designed by modern control theory took shorter time to reach stable, and the system is much faster and it get rid for the steady state error, making the system to have a lower of overshoot. That's all from me. Thank you very much.